Right, I'm going to define a new notion called the greatest common factor, or sometimes the greatest common divisor of two integers a and b. And sometimes you write GCF of a and b, or sometimes you just write a comma b like that in brackets. And this is the largest, this equals the largest number that goes into a and b. It's the largest divisor of a and b separately. And you'll have seen this. In fractions and elementary arithmetic. But I'm just going to talk about it a little bit. Oops. So 12, 18 equals 6, because 6 goes into both 12 and 18. It goes into 12 twice, and it goes into 18 3 times. And you can't get any larger number than 6, because well, the only larger divisor of 12 is 12 itself, and that doesn't go into 18. Let's try 10 and 15. That's going to be equal to 5. And so forth. Let's try 27 and 6, and that's going to be equal to 3, and so forth. Yeah. What I'm going to do is I'm going to give you several ways to calculate this, because this crops up in Olympiad questions all over the place. It's a very common, very commonly used notion. So I'm going to spend quite a bit of time talking about it. I'm going to calculate it in a few ways and give you a whole bunch of results about it. Let's give you an example. I'm going to work out a more complicated example. Let's say 380. So 300. Well, I'm going to factorize it. So it's 3 times 100, of course. So it's 3 times 2 squared times 5 squared. And 80 is, of course, 80 times 10, so it's 2 times 5 times 2 cubed. So I'm just going to rewrite these numbers, 380. It's going to be 2 squared times 3 times 5 squared, comma, 2 to the 4 times 3 to the 0, because there's no factor of 3 at all here. There's no factor of 3 at all there, times 5 to the power 1. And the greatest common factor, well, what we've got to do is to, pretty obviously, is to take the smallest power of each number. So it's 2 squared, because there's a 2 here and a 4 here, so we take the smaller, times 3 to the 0, because there's a 3 to the 0 here. Really what we're doing is we're observing that no multiple of 3 can go exactly into 80, because it hasn't got a factor of 3, times 5 to the power 1. So that's equal to 4 times 5, which equals 20. So you write that down as 300, 80 equals 20. And that's just one way of doing it. There are other ways of doing it, and I'll show you the Euclidean algorithm next. I just want to give a very important special case. Special case is when a comma b equals 1, in which case that they've got no common factor. A and b, oops, A and B have no common factor. There's no number, apart from 1, I guess, that goes into A and B together. And here you say that A and B are relatively prime. A and B are relatively prime, or conversely, A comma B equals 1. And this crops up, this notion crops up again and again and again. So you might say something like 18 and 49 equals 1. They're not prime numbers. Neither of those numbers are prime numbers, but this one here, well, let's take the prime factorization. Well, it's 2 times 3 squared, and that one is 7 squared. So, of course, any number that's a factor of both of those has to go into 2 and 3, 2 or 3, and 7, so that can't happen. Unless it's 1, unless it's 2 to the 0, 3 to the 0, 7 to the 0, I guess. So we've got this notion of relatively prime. And of course, if one of these is a prime number, then we we can put anything we like here, so long as it's not a multiple of 7. Anything equals 1. Anything can go here. Anything not a multiple of 7. And we'll come across this notion again and again and again, simply because this one here is prime. And we'll come across this notion again. So, two numbers are relatively prime if their greatest common factor, or highest common divisor, different ways of saying it, is equal to 1. Which crops up all over the place. Let's try another example. Let's try 64 and 21. Because this one only goes into 2 and this one only goes into 3 and 7. Okay, I'm going to stop there.